In this problem, we have this distributed loading that's this complicated shape. And what we're asked to do is determine the equivalent resultant force and specify its location on the beam measured about point B. Now, point B is going to be right here, and point B actually corresponds to the tip of this high point of the loading. So what we want to do is first we want to go and maybe we look in a table for a shape that looks like this. Now, you're probably not going to find that in the table. So the next thing you need to do is you need to say, can I break this loading up into more simple shapes? And the answer is yes. The answer is I can find a triangle that's right here. I can look at a rectangle that's right over here. And I can look at a triangle that's on top that's like this. So let's remember what it is when we're looking for a magnitude and a centroid of these different shapes. So for a triangle, the magnitude is the area. And the area of a triangle, so my magnitude is equal to my area. And this is going to be 1/2, and let's call this length right here some base, and this area right here height. So it's 1/2 base times height. Now let's look at a rectangle. And a rectangle, if we have a base and a height, the magnitude again is the area, and the magnitude is going to be equal to base times height. All right, so now where does the centroid occur? Well, on this rectangle, it's going to occur halfway along the base, so it's going to be b over 2. So that's where a force would occur. Now, on a triangle, it's a little bit more difficult. From the short side, it's going to occur 2/3 of base. On the high side, this thicker side, it's going to occur 1/3 of the way from the base. So it depends on which way you're looking for. So now that we have the equations that we can use, we can look at finding the magnitude for each of these shapes. Let's start with this triangle. That's this big triangle right here. And I'm going to draw I'm going to indicate what these dimensions are. So this has a height of, or a base of 12 feet. This height, now this height right here is going to be however much of the magnitude is we have of this W, or our loading. So it tells me that right here I have a loading of 800 pounds per feet. So that's what I'm going to use, 800 pounds per feet. So my area, or my magnitude, is going to be 1/2. And I'm going to put units in on this to show you what the units are going to be. 1/2 12 feet times 800 pounds per feet. Okay, so these units right here are going to cancel out. And then I'm going to get 12 times 800 divided by 2. And that gives me a magnitude of 4,800 pounds. So that's the magnitude of this triangle. Now let's look at this rectangle. This rectangle, if we draw in the dimensions that we have, this rectangle is going to have a width of 9 feet. It's going to have a height of this point right here, which is 500 pounds per feet. So the magnitude is going to be 9 feet times 500 pounds per feet. Again, my feet are going to cancel out. And this is going to be equal to 9 times 500. So it's going to be 4,500 pounds. All right. And finally, let's do this last triangle that we have. I think I put it in blue. So with this triangle, well, we know this length right here is still 9 feet. Now, what is this height? Well, this height is not 800 anymore. This height is whatever this length right here is. So this length right here is going to be equal to this 800 minus the 500. So this magnitude is going to be 1/2 of 9 times this we said was 300 pounds per feet. So 1/2 9 times 300 is going to be 1,350 pounds. So now we have the magnitudes of all of these distributed loadings. We just need to figure out where they actually occur. And to do that, I'm going to draw this representation of what my beam is. This is going to be point A, and this right here is going to be point B. So I know, well, I'm going to draw all of these in. So first, my magnitude of this triangular loading, it's going to occur 2/3 of the way from this 12 feet. So 2/3 of 12 is going to be 8. So this distance from here to here is going to be 8 feet. Okay, now let's look at this rectangle right here. This rectangle is going to be, well, we know that at the rectangle it occurs halfway through the rectangle. So we know this distance from B right here is going to be 4.5 feet. Then finally, we have this last triangle. This last triangle, if we look at the small sides over here, so we know that the triangle from it's going to be 1/3 of the way from the bigger side. So this is going to be 1/3 of 9. 1/3 of 9 is going to be 3 feet. So we're going to have this other magnitude right here. This is a little bit smaller. And this is going to be some distance that's, put the distance right here, well, probably closer to here. But this distance right here is going to be this 3 feet. So these are the 3 forces that we have for each of these smaller loadings. So let me put in what the magnitudes are. So this magnitude is 4,800. This magnitude is 4,500. This magnitude is 1,350. But we're not done. What we're asked to do is we're asked to find the resultant force and specify this force of all 3. So we have to put all 3 of these forces together, and then we have to figure out how far away this resultant force is. So we'll have some force, well, let's say it's on this side of B. We don't know what it is, but we're going to say it's on this side of B. We're just taking a guess. If it's negative, it means it's on the other side, and it's going to be some distance of X away from B. So let me actually redraw this just so we don't have that extra force, but we want to now condense everything into one force, and this right here is point B, and we want it one force that's some distance X away from B, and this is going to be my resultant force. So how do I get my resultant force? Well, I have no loading in the X direction, so all I'm doing is adding up my forces in the Y direction. So the sum of, well, my force resultant in the Y is going to be equal to the sum of the forces in the Y. And this is going to be equal to minus 4,800, minus 1,350, and minus 4,500. So let's add those together. 4,800 plus 4,500 plus 1,350. that's equal to 10,650. So we know this force right here needs to be 10,650. But now we need to figure out how far away this force occurs from B. To figure that out, we need to sum our moments. Sum the moments of my reaction force is going to be equal to the sum of my moments about B. The sum of my moments, the sum of the moments of my reaction force is going to be this 10,650 if I'm going this way. So 10,650 times x is going to be equal to all of these guys. So we need to know what this distance is. So this distance right here is 4. So that will be this force right here will be 4,800 times 4. Then this will be minus 1350 times 3. And then we'll have minus 4,500 times 4.5. And again, how do we know if they're positive or if they're negative? Well, if we rotate and they go head first, that means that it's positive. If we rotate and they go tail first, or this, that means they're negative. So now we just need to solve for what x is. Let me move down just a little bit, give me a little bit more room. Just one more line. And I'll have 4,800 times 4 minus 1350 times 3 minus 4,500 times 4.5. I want to divide this by 10,650. And I get that x is equal to minus 0.479. And we're in, so let's get these units right. So this right here is in pounds. This right here is in feet. So this is in pounds. And this distance x was negative. So what this actually means is that this force is on the other side of B. Well, I'll leave that there. But this means that my force, if this is B, my force acts over here. It has a magnitude of 10,650 pounds, and its distance from B is, in this picture, exaggerated, but it's 0.479 feet. If this had been positive, then this would have been correct. So hopefully this helps you figure out how you can solve a composite distributed loading problem.